Hello everyone, welcome to this video looking at finite limits at infinity. So we talked quite a bit about limit as x tends to a, f of x being equal to L or equal to infinity or minus infinity. And we also had one-sided limits, so from the right or from the left. But we never talked so far about what happens as x tends to infinity or as x tends to minus infinity. So let's look at that and see how it works. And so let's get started. So let's assume that we have some function f which is defined on an interval from a to infinity. So all we're saying here is that f is defined for all sufficiently large values of x. So say it's defined for all x bigger than 3 or x bigger than 100 or x bigger than 1,000 or whatever. We don't care about small x, we just care that it's defined for large x. So before, remember, we used to say that x is defined close to a. Now close to infinity doesn't make any sense, but we're saying x is defined for all sufficiently large values of x instead. And let's suppose we can make the function of f of x as close as we like to a number L by making x sufficiently large. So notice here, it looks a lot like the definition of limit x tends to a, f of x equal L. But because now x is not getting close to a, x is tending to infinity. So the x sufficiently close to a becomes x sufficiently large. So we just took out one of the ingredients, we added in this ingredient of x sufficiently large because we're interested in x going to infinity. Okay, so suppose we can make f of x arbitrarily close to L by making x sufficiently large. Then we say that f of x tends to L as x tends to infinity. And we write the limit as x tends to infinity, f of x equals L, or f of x tends to L as x goes to infinity. So notice that whenever we look at these limit definitions, there are many cases where we can combine to get them. But there are basically two blocks, right? Where what we're trying to make or what the value is going to be. So f of x arbitrarily close to L, or f of x arbitrarily large, or arbitrarily large negative. And then we have what we control. So here we're making x sufficiently large, and the other definitions we had x sufficiently close to a. So you have to choose your two building blocks and put them together in the right way, and then you'll get the appropriate limit definition. So here is the idea in a picture. So we're saying that f of x should tend to L as x tends to infinity. And we're saying that that means f of x can be made arbitrarily close to a number L. So here is L on the y-axis. And arbitrarily close to L would mean whatever band we draw around y equals L, the graph eventually is going to lie inside there. I don't care for this example it does, right? However close, however narrow that band we draw, we can make the graph stay inside provided x is sufficiently big. So here, for instance, I drew a value of x that would work for all the values after, it will stay inside the band. And notice it doesn't matter if the function keeps crossing y equals L, that's completely fine, right? It can go up and down or whatever. All we care about is that we can make the graph as close as we like to L, provided we just look far enough along in time. Okay, and of course there are, like we talked about, different variants of this. So we could define the limit as x tends to minus infinity, f of x equals L. So we just have to choose the right building blocks where x is made large negative. So this would say, okay, so our target is f is close to L. So we would say we can make f of x arbitrarily close to L, provided x is sufficiently large negative. So for all sufficiently large negative x. So you just have to choose the input and the output. And most of the limit laws that we talked about in 2.3 on the limit laws work with x tends to a replaced by x tends to infinity. For instance, the sum law, the limit now, instead of x tends to a, we can say the limit is x tends to infinity of f plus g is the sum of the limits. Similarly with differences, with products, with powers, with quotients, provided the limit of the bottom is non-zero and all that kind of stuff. So we can use, again, all those rules, but now with limit as x tends to infinity, or limit as x tends to minus infinity. Okay. So next we have the definition of horizontal asymptotes. So a line y equals L. So remember, y equals L is a horizontal line. So it's called a horizontal asymptote if one of the limits as x tends to infinity or as x tends to minus infinity equals L. So contrast this with vertical asymptotes. So we said x equals a is a vertical asymptote if one of the limits at a, so either the right limit or the left limit at a, was plus or minus infinity. So with vertical asymptotes, we were looking at what we can sub in, where we can take the limit to get something that's plus infinity or minus infinity. With horizontal asymptotes, we're directly subbing in, we're taking the limit as x goes to infinity or the x goes to minus infinity, and we're seeing what we get out. Okay, so notice they are both slightly different. And as we said before, asymptotes are lines. So if you're asked the equation of the asymptote, it should be an equation y equals L for horizontal or x equals a for vertical. Okay, here is a simple example. For instance, with inverse tangent x, the graph looks something like this. As x tends to infinity, inverse tangent tends to pi over 2. As x tends to minus infinity, the inverse tangent tends to minus pi over 2. And don't worry too much if you forgot the graph, you can just trust me that this is what it looks like. So notice, however close we want to make the graph to pi over 2, say I were to draw a small band, eventually the graph is going to lie inside there for all big enough x. And similarly with minus pi over 2, eventually it will lie inside there for all large negative x. Okay. So y equals pi over 2 and minus pi over 2 are the horizontal asymptotes. Okay, and since we have all these ingredients of the limit laws for combining infinite limits, it makes sense that we need a couple of basic limits that we can start using. So one useful fact is that if we look at the limit of 1 over x to the r as x goes to infinity, then that should be 0. And okay, so some examples would be, say, r equals a half. We will be saying the limit of 1 over square root x is 0 as x tends to infinity. If r was 2, we would be saying the limit of 1 over x squared is 0 as x tends to infinity. You know, if r is 100, limit of 1 over x to the 100 equals 0. But notice that we want r bigger than 0, because if I tried to take r equals 0, for instance, I would have 1 over x to the 0. I would have 1 over 1. Just 1, it wouldn't be going to 0. If I have r less than 0, say I had minus a half, 1 over x to the minus 1/2 would become x to the plus 1/2, and that would not go to 0. That would go to infinity, which we'll talk about next time. So we have to be careful with the r bigger than 0, but more or less this is useful. And okay, how about the limit with x tends to minus infinity? It's the same story, but we have to assume that x to the r is defined for negative x. So we have to pick the right values of r. For instance, r equals 1/3 would be fine because the cube root is always defined. But if I pick r equals a half, well, then x to the half, that's square root of x, that wouldn't be defined for negative x. So it's the same story, provided x to the r is defined for negative x. Okay, so for example, here is the graph of 1 over x that you probably know. If we look at 1 over x as x tends to infinity, so this is using r equals 1, right? 1 over x to the r becomes 1 over x. As x goes to plus infinity, it goes to 0. As x goes to minus infinity, it goes to 0. So the line y equals 0 is a horizontal asymptote. And also we know from several times ago that x equals 0, that the y-axis is also a vertical asymptote. So the horizontal asymptotes are horizontal, the vertical ones are vertical. Okay, so let's look at some examples using algebra and limits. So for instance, let's try to find the limit as x tends to infinity of 4x cubed plus 6x squared minus 2 divided by the denominator here. And if we were just to try to naively figure out, what is happening, well, if x is tending to infinity, that means x is going to be a very, very large number. Here, the top is a very large number, and the bottom is also going to be a very large number. So we need to do something. We need to do some kind of algebra. And the trick here is to divide the top and bottom by the highest power of x. So we try to rewrite it in some way so that we can get a grip on it. So let's divide top and bottom by x cubed. Then we get this expression in the middle. And now the advantage is that, for instance, 6 divided by x, we can use the rule we talked about to say that goes to 0. 2 divided by x cubed, we can use the rule we talked about to say that goes to 0. So the top is going to go to 4. And then similarly, the bottom is going to go to 2. And then we can use the limit laws to say, the limit of the top divided by the bottom is the limit of the top divided by the limit of the bottom. So this is going to go to 4 divided by 2, which is 2, okay, which we can do. So if looks like we're getting infinity over infinity, try if you can to use some algebra to rewrite it. And eventually we'll have other tools for doing this, but that's going to be the main tactic right now. Okay, here is another example. Find the limit of the square root of 9x squared plus x minus 3x. Again, if you sub in x, it's a very large number. If you think just kind of in your head what's happening, if x is a large number, then x squared is going to be a large number. At that 9x squared plus x is going to be a large number. Take the square root of that, I'm still going to have a very big number. But also, if x was a big number, then 3x is a big number. So just naively, I have a large number minus a large number. I can't say anything. So I have to try to rewrite it somehow using algebra. And the trick is to rationalize the numerator. And it looks like because there's a fraction, there isn't a fraction. It doesn't look like it makes sense to rationalize, but we can just make it a fraction by writing, whatever we have as that thing divided by 1. So here we write our expression as the same thing divided by 1. And then it makes sense to rationalize the numerator. So we multiply top and bottom by the conjugate of the root on the top. And then we expand and we cancel. And so we get to x divided by square root of 9x squared plus x plus 3x. And okay, now we have something that looks like infinity over infinity. So we go back to what we said before. So what is the highest power on the top and on the bottom? So on the top, it looks like I have x. And on the bottom, it looks like I have an x squared. but it's actually inside a square root. So that actually becomes, or is kind of like the order of x. So my highest power is kind of x, so I should divide the top and bottom by x. So when we do that, we get 1 over the square root of 9 plus 1 over x plus 3. And now it makes sense just to take the limit as x goes to infinity, right? If we do that, the numerator is just 1. And the denominator, if we start with the inside of the square root, as always, start inside and work your way outside if you can. 9 plus 1 over x is going to go to 9, because we know 1 over x goes to 0. The square root of that goes to the square root of 9, so it goes to 3. And then we had the 3 from before, so we're just going to get 1 over 6. Okay. So with fractions, as x goes to infinity, if they have the same degree on the top and the bottom, then you should divide top and bottom by the highest power of x. If the bottom has the highest degree, then it should go to has a strictly higher degree than the top, then it should go to 0. If the top has a strictly higher degree than the bottom, then it should go to infinity, which we haven't talked about yet, but we will get to. Okay, and here is one more example. So remember when we had compositions? When we talked about finite limits, the tool to try was continuity, and we said if our outside function was continuous, we can just bring the limit inside. And here that doesn't work, it doesn't quite make sense because we're looking at limits as x tends to infinity. So we didn't define any kind of continuity like that. But let's just try to break down this example and work our way from the inside out. So the limit as x goes to 0 minus, so 0 from the left, of e to the 1 over x. So let's think of e to the 1 over x as e to the t, where t is 1 over x. And then let's see what happens as we work our way out. So in this problem, x is going to 0 from the left. And then t is 1 over x. So we have 1 over x, and x is going to 0 from the left. That will go to minus infinity. Okay, if we remember the graph of 1 over x. So another way of saying x goes to 0 from the left is saying t goes to minus infinity. And then as t goes to minus infinity, remember we're interested in e to the 1 over x, but we rewrote that as e to the t. So now we have e to the t, and t is going to minus infinity. Well, if you remember the graph of e to the exponential function, as the input goes to minus infinity, the exponential function goes to 0. So e to the t is going to go to 0. And now we worked our way, but t was 1 over x, right? So we worked our way to the outside. So in other words, as x goes to 0 from the left, okay, e to the t is going to minus infinity, but that's just another way of saying e to the 1 over x goes to 0. Okay, so the moral is to start from the inside and work your way out. And if you don't like introducing more variables, which I think makes it a little more confusing, just look at it, e to the 1 over x. X is going to 0 from the left. If I start with the inside, as x goes to 0 from the left, 1 over x is going to minus infinity. Now I have exponential function, and something is going to minus infinity. I think of my graph of the exponential function. Okay, if I insert a very large negative number, where am I going to be? I'm going to have a very small positive number. It's going to go to 0. Okay, so with these ones, start from the inside and work your way outside. Okay, that's it for this time. Thanks, everyone. See you next time.